Hello, this is the little lecture over 6.3. I did a little bit of 6.3 in class the day before the test, and so this is kind of a continuation of that. And I think if we can handle this, I think you pretty much can handle 6.3. Remember the E, though, is 2.718. I didn't give you any one of those up there, but it works exactly the same. So look at your notes from that part as far as 6.3 is concerned on the E. And but anyway, a couple of problems, we want to graph them, and we're going to also find the domain and the range while we're at it. Now, the domain and the range, we're going to do that after we get the good graph put on the Cartesian plane. So now, f of x equals 3 to the x minus 1. Now, this is kind of like transformations. And if you remember, 3 to the x looks like this. This is, again, we talked about this last time. You put 3 to the 0 in, that's 1. 3 to the first is 3. 3 to the second up here is 9. 3 to the negative 1 is 1/3. So this graph here is 3 to the x. That's 3 to the x. Now, the 3 to the x minus 1 is going to be a horizontal shift 1 unit to the right. So that's when we talked about the transformations back in 3.5. And if you don't remember the transformations, you can always do this by a t-chart, just like what we did before. You know, you just like with 3 to the x. We can make a t-chart here and put 0 in, and then 3 to the 0 minus 1 is going to be 3 to the negative 1, which is 1/3. If you put in 1, 1 minus 1 is 0, 3 to the 0 is 1. So you can do it that way as well, just by doing a plot in a bunch of points until you figure out what the graph looks like. I like looking at the basic graph and just taking this graph and just point by point, just moving it 1 unit to the right, because that's what the x minus 1 does. So I'm going to use this as a copy. Instead of 0, 1, it's going to be 1, 1. Instead of 1, 3, it's going to be move it over 1 more, be 2, 3. Instead of negative 1, 1/3, it's going to be it's going to be 0, 1, 1/3. So, which is what we said already. So 0, 1/3. So that's the graph here. So all I did was I take the basic graph and move it 1 unit to the right. That's all it is. Now the domain, of course, as you can pretty much tell, there's no vertical asymptotes, so exponential functions are going to be pretty much all real numbers. So the domain will be the reals, and then the range, remember, is the y-coordinates, and the y-coordinates are going to be above the x-axis, because if you notice, there's no part of the graph below the x-axis. So even though the graph doesn't technically hit the x-axis, it's above it though. So the range is all positive numbers. So to write that down, is going to be 0 to infinity. And so that's the answer. So here's the graph, here's the domain, here's the range. So that is one example. That's pretty basic. Now let's look at the next one, negative 2 to the x plus 1 plus 3. Now this is applying 3 transformations to the graph of 2 to the x. Now 2 to the x, if you remember, again, the day before the test, this is going to be 2 to the x, so 2 to the 0 is 1. Remember, they all go through 0, 1. And then 2, 1, you put 1 in, you'll get 2, so it's 1 comma 2. And so after a few points, it looks like this. So you're like, well, that's 3 to the x. No, it's not. It's not quite as steep as 3 to the x. And so we're going to take this graph, which is 2 to the x, and we're going to apply 3 transformations. We're going to move it 1 unit to the, what do you think? It's going to be left because it's x plus 1. The minus 2 flips it upside down, and the plus 3 moves it up. Now, there is, it's above the x-axis here. So what we're going to do, when we move it up above 3, it changes where it levels off at. If you remember from class, it's called a horizontal asymptote. So there's going to be a horizontal asymptote right there. So yeah, but what's the horizontal asymptote on the previous one? 1, 0. Y equals 0 because it's right on the x-axis. You don't go up, you don't go down. So there's a horizontal asymptote on y equals 3 on this one. So you take this graph right here, move it 1 unit to the left. So you take this graph, move it 1 unit to the left, turn it upside down, and then move it up 3. So what's going to happen is it's going to look like this initially. Move it 1 unit to the left right there, and it's going to look like that. But that's not the answer. Because what that does, it takes into account everything except for the negative. The negative, remember, turns it upside down. So you take this point right here, and it looks like so. So there's your answer. So right there. So that's the actual graph. So that takes into account 1 unit to the left, turn it upside down, and add 3 to it. So, and that's how you do it. And the domain, of course, again, is all real numbers. There's no vertical asymptotes. The range will be less than 3. This is there's like a ceiling there. So here's a ceiling right there, and it doesn't get any higher than 3. It levels off at 3 when the graph heads that direction. So it's going to be 0 to 3. Notice there is no bracket on the endpoint because you never get there. Just like this one here was 0 to infinity because you never get down to 0. You get closer and closer, but you never get there. Now you have, well, what if they ask for the horizontal asymptotes? Well, the horizontal asymptote on that one would be y equals 0, and the horizontal asymptote on that would be y equals 3. Now on this one is another section there on this section, another set of problems anyway, and what's to solve each equation. Now, I really didn't have time to talk about this the day before the test, but I do want you to remember that if you have two numbers that's raised to different exponents but have the same base, that just means that the exponents have to be the same. So a very simple example that would be something like if you think of 2 to the x equals 2 to the third. Obviously, 2 to the x equals 2 to the third. X would have to be 3 because 2 to the third equals 2 to the third. And that's the concept you're going to be using right here. If 3 to the x plus 1 equals 3 to the 2x minus 5, the bases are the same. So therefore, you can just set the exponents equal to each other. And once you do that, you just solve for x normally. And this normally is easy because you just isolate the x. So subtract x over here, so you get x minus 5 equals 1. And then, so I subtracted this x over here. And then add this 5 over here, so 5 plus 1 is 6. So x equals 6. So that solves this equation. What that basically means is if I put 6 back in, the left-hand side equals the right-hand side. And obviously it does. 6 plus 1 is 7, so it'll be 3 to the 7th. And then 2 times 6 is 12. 12 minus 5 is 7 as well. 3 to the 7th equals 3 to the 7th. You betcha. So, and this one is a little bit the same thing, but it's a lot more difficult. So you eventually have to get to the same point, but you don't have it yet. This is base 4, this is base 2, this is base 16. So ultimately what you have to do is get it in this form, b to the n equals b to the n. So yeah, you're going to have to get this under the same base. So there's a lot of rules of exponents that you have to apply. 4 is the same thing as 2 squared. That 4 right there is 2 squared. Then you tack on the x, so it's be 2 to the 2x. So 4 to the x is the same thing as 2 to the 2x. And of course 2 to the x squared, you can't really do anything with that. Now 16 is of course 4 squared, but that doesn't help me because if I make 16 4 squared there, then I still don't have the same base. So I'm going to change 16 to something else, and that's 2 to the 4th. So that's what 16 is. But what about the 2? Well, you got to tack that on. So it's 2 to the 4 times 2. So the right side becomes 2 to the 8, because 4 times 2 is 8. Now the left-hand side is tricky. Now remember, 2 to the x, 2x times 2 to the x squared is not 2 to the 2x cubed. You don't multiply the exponents. You add the exponents. Well, why is that? Well, because of the product rule. So as a reminder, just remember this, that if you had x squared times x to the 5th, that is x to the 7th, not x to the 10th. And you're like, why not? Why is it x to the 10th? Well, because x squared is 2 factors of x, and x to the 5th is 5 factors of x. And how many factors of x do you have? Is 7, so it's x to the 7th. That's why it's x to the 7th and not x to the 10th, because it's just a counting of the factors of that expression. So this has to follow the same rule, even though you can't really add the 2x and the x squared like you can the 2 and the 5. That's okay. You just keep them detached. So it'd be 2 to the x squared plus 2x. So you can't add x squared plus 2x because they're unlike terms. Now, guys, this is one of the tougher ones in this section. So you're like, if they're all going to be this hard, no. I gave you a really simple one, and I gave you a really difficult one. A lot of them was going to be kind of in between of those. So you're like, what do I do now? Well, you do the same thing you did on example 1 I gave you. Now that you got bases the same, and you can't do this until you get the bases the same. But now that you got them, you can actually drop them off. So it'd be x squared plus 2x. This exponent must be equal to this exponent of the 8. So remember, b to the m equals b to the n if and only if m equals n. So in other words, a lot of people just say, well, you're dropping off the bases. You're canceling out the bases. That's not really what's going on, but that's what a lot of people think of it as. The reason you can do that is because exponential functions are one-to-one, and so therefore you can do that because they are one-to-one. So, but if you want to be one of those people who think, oh, you just drop off the bases and you don't care which way, right, that's fine. That's fine, because that's not a major important factor here. So x squared plus 2x equals 8. So it's quadratic, and you got to solve it. So you set it equal to 0. Because that's how you solve quadratic equations. You got to set them equal to 0. It's not like a linear equation. And then hopefully it'll factor, and it does. It factors to x plus 4, x minus 2. And you're like, well, what if it doesn't factor? Well, you know what to do. You have to use the quadratic formula. So, and that'd be bad news because the problem is hard enough as it is. And now you'd have to use the quadratic formula. Hopefully they don't do that. They won't do that to you. They'll make this step right here a factorable step. So x equals negative 4. And x equals positive 2. Now, a lot of people think that negative 4 is not going to be allowed because it's negative. And this is not true, because just because the answer is negative 4, okay, doesn't mean you discard it because it's negative. Okay, this is not a square root or anything like that. So negative 4 is fine, and positive 2 is fine as well. But like I said, this is one of the more difficult problems. As a matter of fact, I think this is actually number 71 in your homework assignment. I just made this one up. But anyway, so these are some questions that you might see out of 6.3. But again, on the first part, that's probably the most tricky part, is remembering the transformation. So the good news on this part here is you've done it. It's just a different graph. So back in 3.5, we were taking parabolas and moving them 1 unit to the right. Or we were taking a cube root function and moving it 1 unit to the left, flipping it, and then moving it up 3. But that was with the cube root maybe, or square root, something like that back at 3.5. Well, now we have another graph to do that with. That's all it is. It's just a different image to do the same old stuff. Moving them 1 unit to the right, 1 unit to the left, maybe move it up 3, maybe flip it over, maybe stretch it, maybe compress it. But you're still doing the same thing, just with a different parent graph. You remember my terms I use in class. So. But anyway, that's 6.3. It's not all of it, but I think that will get you good and started in this section. So enjoy.